then let's get started. Welcome everybody, and a warm welcome to our speaker, Hans-Peter Arp. So I had to go back in memory lane to think about when Hans-Peter and I first met, and this was, I think, in 2004. So Hans-Peter is from Canada originally, but then he went to Tübingen, to Thorsten Schmidt's group, to do his master thesis, and he contacted me, and we worked on some fugacity modeling of MTB and its transformation products, and Hans-Peter even wrote the paper on it, so that was nice. And then he decided to come as a PhD student, actually first here to Eawag, so with René Schwarzenbach and Kai-Uwe Goss, and then he was one of those who moved then with them to ETH, where he then finished his PhD in 2008. And from then on, he moved to Norway with his wife. He went to NGI, so that's the Norwegian Geotechnical Institute in Oslo. And he's been there ever since, but kind of risen through the ranks to become an expert advisor now at NGI. And he's now also an adjunct professor at NTNU in Trondheim. Hans-Peter is an environmental chemist by training. He's also always been very interested in sorption, early on already in fluorinated compounds and the somewhat different sorption behavior of fluorinated compounds. I think this pretty much then probably also led to what you're very interested in now, persistent mobile and toxic substances, and fluorinated compounds are an important group of PMT chemicals, but I learned that you're also very interested in plastic pollution, and especially also in chemicals in plastic materials, but also other materials like e-waste and street tar and so on. What I always found fascinating about Hans-Peter is that he's not only a very good environmental chemist, but he also, if I remember correctly, won an essay writing competition as a PhD student at ETH, and I remember some kind of poetry or PowerPoint slam and karaoke going on. And he's just been an extremely broadly interested mind, a great communicator. And so that's why it's really exciting to have you back. And I'm really looking forward to hearing kind of what's going on at the front of PMTs. Thanks.
Oh, yeah. Well, thanks so much, Catherine, and thanks for that great introduction. And yes, it is very good for me to be back. I had to start with some pictures from that time. So that's me when I started in 2004 in the corner there. I see the Eawag in the background, the people I was with. And as Catherine said, I then moved to ETH Zurich, and then that's René Schwarzenbach there, and that was at my graduation. And so, yeah, a very special time for me. And I would say, especially that first year at the Eawag. The first year at the Eawag was very formative in my career. I think that's what changed me from kind of the student to being a researcher. And so it was very formative years for me. And also around that time, there was a change in logos I thought was interesting. Because this was the logo that was there when I started. And then around the same time that we were moving, all this reconstruction was happening, they changed it to this logo. And we were all looking at it saying, what the heck do the 3 dots mean? I don't know if that's still been solved. If somebody tells me, let me know after this, because I'm organizing my talk based on these 3 dots. So the first part of my talk, the first dot is about the increasing contamination of PMT substances. Then I'm going to talk about regulatory developments. And then the final dot is how to reduce pollution. So this is the first thought about the increasing contamination and why I'm so interested in PMT substances. So I want to start out with like this kind of a story, because the origin story of the PMT is the PBT, which means persistent, bioaccumulative, and toxic. And PMT is persistent, mobile, and toxic. But in 2008, a Dutchman by the name of Pim de Vogt said, the European REACH legislation will possibly drive producers to innovate their products, possibly to develop newly designed chemicals that will be less persistent, bioaccumulative, and toxic. This may result in higher mobilities of chemicals in the aqueous environment. As a result, the drinking water companies may face stronger demands on removal processes as the hydrophilic compounds inherently are more difficult to remove. So this was about PBT starting a shift in what kind of chemicals are made. And what we've seen in the monitoring data, also in the Netherlands, is this has been broadly supported. So with these, here's me giving some water to my son, and what these purple dots are the number of persistent and mobile substances that they find monitored in this very important drinking water source in the Netherlands, Norway, something like this. And the black ones are those that are exceeding the EQS threshold, or the threshold that they think this is going to be a problem for their consumers. So this is the trends in how they monitored over the years, and they saw a really big increase around this time of the PBT coming into force. This is around 2007, 2008, and it's been more or less increasing each year. And this was also the cost of investment that they have to do in the water treatment facility at this Norway to remove these chemicals to get to drinking water standards. And this is also increasing. So this is the burden that's being put on water producers. So we can ask ourselves, well, how do these chemicals get in there in the first place? Just to think conceptually, how do these chemicals get from a factory somewhere to my son's drinking water bottle? And obviously these chemicals were made for uses in products. It can be a plant production product. It can be in a toy. It can be in a building material. But some of these, either through their synthesis or their use, they'll be emitted into the environment. And if they're persistent in the environment, they might go continuously forward and eventually to a water treatment production facility where there might be something like just basic sand filtration, or maybe they have activated carbon. But if it can break through there, I can go to my son's drinking water bottle. And the chemical properties that we're interested in this context are persistent and mobile, persistent enough to survive the environment, this amount of time that it takes to make that journey, and mobile because it actually has to move and through all these barriers. And if any of these compounds are toxic, then we have a problem. And that's what the basis of what a PMT substance is. Now I'll just give you some more concrete examples, and one is PFAS. It's mentioned a lot in this context. So this was a survey of PFAS in global tap water, where it was just simply tap water from cities around the world were sampled. They were sent to the University of Montreal. I only helped the story by supplying the Oslo sample, but they were sent to the University of Montreal, and they looked at what were the PFAS concentrations. And what they could find is that recently the Danes had a drinking water limit of 2 nanograms per liter, or 0.002 micrograms per liter. And there are many cities that exceed this concentration in their tap water. Now, even more recently, the US EPA has looked at these PFAS, and they found that actually they're a lot more toxic than we originally thought once we think of immunotoxicity. And they came up with even lower drinking water limits of, or we're talking into the picograms per liter. And if you're talking about what cities have drinking water, tap water that exceeds those concentrations, the answer is all of them. The entire globe has drinking water concentrations that are not safe for PFAS. So, there we go. And we can also, another example that I want to give you is one of the substances I'm most interested in, and this is trifluoroacetic acid, which is also a PFAS. This is the structure over here. It's one of the smallest ones. It just is one perfluorinated carbon, and it's acetic acid. It's like the acetic acid except perfluorinated. Now, there's recently done a survey in Denmark of all the groundwater wells, and they found PFAS in most of them up to a concentration of 2.4 micrograms per liter. So it's distributed in the groundwater of almost an entire country. But it's been seen in many other environments. They look at this a lot in Germany, and they find it in tap water up to 20 micrograms per liter, and in river water up to 120 micrograms per liter. There was a study where they looked at this in China, in the blood, and they find that this was detected in 97% of those samples in their blood at 8.5 micrograms per liter. But the question is, where did this trifluoroacetic acid came from? And there's many different sources. So some of my colleagues call it a substance from multiple sources. One of them is plant protection products, when they have these little N groups that are CF3. These are high production plant protection products that will degrade to trifluoroacetic acid. And another potentially larger pool, I don't know if there's any, I think this is a larger pool, is from the refrigerants. So these are refrigerants that are allowed to be used in still, even after the recent amendments to the Montreal Protocol. So they're used in refrigerators, things like this. They're very high production chemicals, and they go into the atmosphere, and in the atmosphere they become degraded to TFA. And this is one of the reasons why we're finding so much trifluoroacetic acid in rain. So those are two major sources to groundwater. But it's not just groundwater, it's also accumulating in the ice cores. If you go high up in the Arctic, if you look at the ice cores, you see the sudden accumulation that corresponds by the time these chemicals were introduced in refrigerants on the Montreal Protocol. So right now we're just seeing this rapidly, exponentially, I would say, increasing concentration of trifluoroacetic acid. Some people will say trifluoroacetic acid is natural, but just these trends showing that the only reason for their presence is because of the new synthetic precursors of these chemicals. Now, something I want to say about this is that the lowest, something happened with my slide, but the lowest known observable concentration for these chemicals is for a microalgae, it's 120 micrograms per liter. So you can look at these concentrations and say, oh, we're nowhere near that kind of toxicity. This has only been exceeded in some hotspots. But that's the lowest no effect observable concentration so far. What we've seen with PFAS, just like that example I gave you with the PFOA and the Americans having this low limit, they're always finding these things are more toxic than they originally thought. So that the effect concentrations decrease. And at the same time, the concentrations we're observing in the environment increase. And the huge problem with this one is if these two ever meet, if we're ever at a point where the concentration exceeds an effect concentration, then there's not much we can do about it. We can't clean it from the oceans. It's non-dilutable because it's already been diluted and will only continue to accumulate. So when you have this type of situation, it's called a planetary boundary threat. And I think TFA should be considered a little bit more seriously because of this. But this is there's some opposition because there's a lot of money to be made in these refrigerants and plant production products. But it's not just PFAS when I talk about PMT. I'm also talking about other ones. And another one is melamine. And this is it's commonly associated with like laminates and resins. But this is found up into concentrations up to 2 micrograms per liter. And this is toxic to kidneys, especially in combination with a chemical called cyanuric acid. So cyanuric acid is another PMT substance that we're seeing quite ubiquitously in drinking water at concentrations up to 0.12 micromilliliter. So in some areas, it's also co-occurring. So this could be, for that population drinking this, cause some epidemiological effects on kidney health. Another one is this carcinogenic solvent, 1,4-dioxane. It's been measured in places like Germany up to concentrations of 0.8 micrograms per liter in tap water. And benzotriazole is another one. This is commonly used in dishwashing detergents. It's used to prevent dishwashers from rusting and things like this. But this is going right from people's sinks and into the drinking water supply, and then they're drinking it again. So there's almost kind of a loop with this benzotriazole. And we find this in areas of up to 0.2 micrograms per liter, which is also exceeding the safe drinking level threshold. So these are other PMTs. And there's likely many, many more. There's many chemicals out there. But for years, we've been dealing with a gap in our knowledge about these chemicals. And this was one of the early publications we had on PMTs and what they are. And we called it Mind the Gap. And one way we like to show this gap is this gap in regulation. So you see these are different regulations that were set up so far, like Stockholm POPs, REACH candidate lists, EU watch chemicals, and these is the DOW value of them. And you can see they all kind of fall into this space. And what you find is there hasn't been many regulations set up for the very hydrophilic substances. And these were, for instance, so-called GAP compounds. And one of the reasons for this is this was outside the space that most instruments could measure things. HPLC and GCMS could not get into this level of hydrophilicity unless there are some dedicated methods. So this is something that they call the analytical gap. But since then, there's been a kind of a revolution in terms of new methodologies to measure these hydrophilic chemicals. So we're looking at new chromatographic techniques like hydrophilic interaction liquid chromatography, iron chromatography, capillary electrophoresis, supercritical fluid chromatography. And in addition to that, we need novel enrichment techniques because often when you're trying to get these chemicals from your sample, like TFA is a good example, it's being extracted at the same time as your salts, like your chloride and your bromide, and you got to try to separate that. But this is giving us analytical capabilities to get into more hydrophilic compounds than, say, reverse phase liquid chromatography. So this has been good, and because of that, we are able to detect more in the environment. So there's been different suspect screen lists for these very mobile compounds. This was a report that I co-authored in 2019, and it's going to be updated very soon. And we also came up with some tools to use REACH data to estimate emissions into the environment. And I know Julian Hollander is working with the transformation products in NVPath from Catherine Fenner to look for transformation products of pesticides. And so now you can have these suspect screens and you end up with a, what is wrong with my PowerPoint? Yeah, now you end up with positive hits. So now we can find more and more of these. And I'm going to give you some examples that have just been found in recent years. And these were compounds that have not been detected in the environment, I would say, before 2018, I think. And now we're finding them not only detected, but in high concentrations and in many samples. I can just point out some of them. This is like a close cousin of TFA. This is trifluoromethane sulfonic acid, it's another short TFA. You find a lot of interesting structures here, these very interesting cyclical structures, because there's not many bacteria that can degrade them. There's a lot of some benzyl sulfonates appear quite commonly, and a lot of these guanidine structures. These are also quite common. So you're finding more of these, and they're finding everywhere, and they're just under the radar. But with these new techniques, they're no longer under the radar, but they're still what we call a monitoring gap because these methods that have been developed are not widely adapted or adopted. So this is from a survey we did of analytical labs in Germany and saying, here's a list of 150 chemicals we think are PMT chemicals. Can you analyze them? Yes or no? And then there was, for 27 compounds, more than 20% says, actually, we measure them on a regular basis. Our clients are looking for these chemicals. We measure those. So this is not what we call a monitoring gap. But then the monitoring gap kind of starts because there was 39 chemicals where less than 20% could analyze. Sorry. So there's some data, but it's not as widely reported. And then there's 58 which labs said they could analyze. They would know how to analyze them, but nobody's ever asked them to. And there was 21. They said we could measure them. We think we know how to measure them. We never tried, but I think we could develop a method. And there are five of these chemicals where they said, no, this is impossible. It's theoretically impossible to measure these chemicals. That was a universal answer. So there's still a little bit of the analytical gap, I would say, over here. But the main thing is that there's a monitoring gap for a lot of chemicals. And there's also a remediation gap because no remediation technology is perfect. Activated carbon will let the very small aliphatic and anionic compounds go through. Anion exchange resins are good for cations, not for anions. Same cation exchange resins are good for anions, not for cations. And you can go to more advanced techniques like nanofiltration or reverse osmosis, but not even these are perfect. You still have some very small molecules that break through. And then you can also use advanced oxidation processes like ozonolysis, but then you have to pay attention to what are the transformation products, because some of those could be PMTs as well. And this was another survey we did of the drinking water treatment facilities in Germany. And we asked of the same list of 150 chemicals, And we also addressed this in addition to surveys. We also did some theoretical calculations. And then we found for 52% of the 150 PMT vPvM substances we identified, they could not be removed with ozonolysis or activated carbon. There were some 15% that could only be removed with ozonolysis, 21% only removed with activated carbon, and there were some that were actually quite easy to remove. But these are also breaking through that remediation barrier I showed earlier. Okay. And, sorry, which one's that? There we go. And this is associated with like a lot of cleanup costs. So if we assume that reverse osmosis is the only technique that works, that activated carbon and is not good enough, then we can look at that. But the cost of reverse osmosis is €1 per cubic meter or 1 kilowatt per cubic meter. And we can do like back of the envelope calculations that if we say there's 200 billion cubic meters per year of industrial wastewater, or 38 billion cubic meters a year of drinking water, then we end up with costs in the range of 200 billion euros per year. And who's going to pay for that? Will this be the polluter? Who's the polluter? There's many polluters. Or is it going to be the taxpayer? It's most likely going to be the taxpayer. This is what we have to claim. But when we talk about what about the energy costs to this now? And this is only going to be increasing, especially with the energy situation we have today, because reverse osmosis requires a lot of energy. And this is also not good for ultimate sustainability. So this is a huge economic burden to society as well. And so to address that, the only way we can really address it, because we're not going to be able to address it with technical cleanup options, is to look for regulatory developments. And that brings me to my second dot, regulatory developments. And the biggest thing that happened here was the EU Chemical Strategy for Sustainability, which specifically mentions PMT chemicals. And so I'm going to begin this dot with another quote from a colleague of mine who noticed that the evaluation of drinking water impacts is not yet explicitly defined in REACH. These should be screening criteria developed for which the responsible authorities could identify the chemicals that could impact drinking water from the REACH registration database. To realize the precautionary principle, it is important to identify potentially drinking water contaminants as early as possible. So that would be in the stage of the actual regulation under REACH. And so what they wanted to do was go about developing a criteria. And this was actually the birth of the PMT concept. It was first presented in 2012 as an idea from Michael Neumann in a CTAC poster, and then further developed in 2015. And very recently, we started talking, and then I started working with them at the Umweltbundesamt to help them with the science behind the criteria. But they came up with these terms: persistent, mobile, and toxic substances, or PMT substances, and also another category, very persistent and very mobile substances. And the idea was, if you had chemicals at the REACH registration level that met these criteria, that you'd already from the beginning, the producers of these chemicals would have to put in risk mitigation measures to make sure that their emissions are controlled. And what we argued to make this as a new criteria is that we had to show that this was an equivalent concern to another set of criteria. And this was the PBT and vPvB substances, the bioaccumulative ones. Because in regulation, it really helps to have a precedent which you can base the new regulation on. The two things that help is that precedent, and the other thing that helps is if what you're suggesting is enforceable. But where you could show that at least it was equivalent was because we could show that these substances are equivalent in terms of the health effects they can cause because they're toxic, their environmental effects because they're toxic. So they have these effects as well. And there's many other effects. And in this paper, to show that there is some equivalency, we used 3 example compounds. This was perfluorobutane sulfonic acid, BFBS, GenX, which is another PFAS, and the solvent 1,4-dioxane. And I'm not going to go through all the criteria that we argue point by point that they're equivalent level of concern. There were 16 points. I'll just mention 2 of them. One is that we argued both have irreversible health effects as possible. Because of the PBT case, they would bioaccumulate in people's lipids in their body, where chronic and acute effects can occur, and you can't really dilute that. And yes, also for the PMT substances, because you get in a situation where you cannot dilute it or treat it from your drinking water supply, so you're drinking it all the time, and that's irreversible. And that's the effects, and you can also apply this to the exposure. It's because the exposure itself is also irreversible once it gets to a certain point, because dilution is not efficient. Yes, so just, but now the next question is enforceability. And how to make them enforceable was we had to show that persistence and mobility are substance properties that you can measure. And there is some precedent for this as well. So if we look at the traditional idea of groundwater contamination, you have industry, they're contaminating their soil, and there's a plume that eventually ends up into the groundwater, drinking water supply of a community. And this is, it goes right into the drinking water well. And very early in this research on transport pathways of pesticides, agricultural chemicals, was this Gustafson ubiquity score, or GUS. And he was doing some column tests and other tests, and he would make this correlation between the soil half-life in days versus the log organic carbon partition coefficient, which is how well that chemical partitions between organic carbon and soil and the water. And then he came up with this function that would show this zone of leachers. These were the chemicals that could make it to groundwater, given a certain context. These were the ones that would not make it to groundwater because they were either degrading too fast or too strongly absorbed to the soil. And in the middle, you had this transition zone because the borderline is a bit fuzzy. So this was a basis, and it was two substance properties that we could measure in the laboratory. These are both lab measurable parameters to make this kind of analysis. And so the PMT criteria is based on this. And after I press this software,
Yeah, exactly.
I'm going to stop using this.
Yeah.
One second. Still it wasn't. One moment. See, this PowerPoint presentation is not mobile.
Can you
Trying,
exit quickly?
trying. There we go. And so to develop, I'll just quickly, to develop this criteria, we took the idea of like the Gustafson idea, and we tried to develop it into two criteria based on the scientific background of why this is justified to use persistence and mobility and reach. And there was also this technical thing about the regulatory criteria and how it should look like. And this is something that was developed into different workshops at different meetings at the European level and sometimes at the German level to try to workshop this criteria and develop it through to get some progress. And briefly, just to walk you through that, the first thing that you do when you have identify organic chemical at reach is you look if it's persistent. So you do that simulated half-life test or another test. And if it is not persistent, you don't have to go further, but if it is persistent, you have to do a mobility assessment. And when you do that, you can have two types of substances. You can have very persistent and very mobile, depending on what your results are, or it can be just a PM substance. And then you look for toxicity, and if it's toxic, there can be a PMT substance. So there's some substances that are both PMT and vPvM, and some are just one of the two. And the criteria for persistence, these are taken the exact same as the PBT criteria. So these are the exact same persistence criteria that's been on the books for a long time. And as I said before, if there's a precedent, it's usually accepted. It's already accepted in regulations, and there's no reason to comment on it because that discussion has already happened. But for the PMT, we decided to use the exact same criteria, which included the soil criteria of 120 days as persistent, and 180 days is very persistent. But we also consider persistency in water or even sediments. And it just has to fill one of these criteria to be considered persistent, just one of them, or very persistent. And then for mobility, what we were working with when we were developing the concept was a log KOC value between a pH of 4 to 9 to account for ionizability. Of less than 4 was mobile, and less than 3 was very mobile. And this was what that was submitted to some EU level meetings. but the European Commission came back when they made the chemical strategy for sustainability. It was last year, 2021, they made a proposal that pretty much adopted this definition of mobility exactly like we suggested, but they decided to move it down one notch. And it's 3 for mobility and 2 for very mobile. But this is what's being on the draft proposal right now for the regulation of the CLP regulation. And I should say the CLP regulation, that's the labeling hazards one. So if that goes through, that would mean that all chemicals have to be tested if they're PMT or not, or vPvM, and if they are, they have to put the warning label on there. It doesn't mean that they have to restrict or do anything about it, it just means that this has to be put on as a warning label. But just to show some more empirical proof, because this was important to convince people who are against the criteria. At the top graph, we have surface water detections of persistent substances kind of plotted on a histogram. And you can see on the top plot that you will find in surface water many persistent substances with high log KOC values. But when you go down to the detected persistent substances in drinking water, these cutoff make more sense because there's very, for the persistent substances, there's little that above log KOC4 that we could find. If we include non-persistent chemicals, you can find some high KOC ones, but there's different explanations for that. But most of the chemicals would meet the European Union's criteria for mobile or very mobile. So it is getting the majority of the substances we're seeing in drinking water, but there is some discussion, some trade-offs about where to put that criteria. Another reason why we like this using KOC is that there is a lot of precedent in existing regulations. For instance, the bioregulation also includes KOC as a measure of mobility. And the United Nations Food and Agricultural Organization and their risk assessment classification of mobility, they're also including KOC. And also from leaching tests, you can correlate leaching test results with KOC. So there's a lot of precedent to use it. So it's really just a question of where are you going to set that border? And that's more of, I think, the socioeconomic analysis of how much is this going to be enforceable, what kind of market impacts this is going to have. So that was weighed, I think, a lot more on the European Commission's decision than us, because we didn't look too much on that ourselves. Another question is how many PMT, vPM substances are out there? And based on this criteria, what we find is that when we looked at the REACH registration database, and this is a paper that just came out a few months ago, that maybe 3% of the chemicals on the REACH registration base we think are PMT, vPM based on our initial screening, again using the UBA criteria, but you see there's 41% of chemicals that we don't really have enough data to do a decent assessment if they are PMT, vPM or not, so there's a huge data gap. If we go over to the REACH registered substances that we detected in drinking water, we find that 30% of them are PMT, vPM, and we have a lot more data on these compounds, so there's only 18% that we don't think are PMT, vPM. And you also see there's a lot of REACH chemicals that were detected in drinking water that are not PMT, vPvM, and this is usually because they were not persistent and used in high volumes. So an example here would be caffeine or something like this. It's just the volumes are so high that it can break through to drinking water despite not being really persistent. But we say we're not really concerned with these ones because it's ultimately the persistent chemicals that we find the most problematic for the environment and exposure. So, but this developed rapidly. So I mentioned briefly how we had to workshop this criteria at different EU level meetings, but it's really at an exciting stage now because the European Commission have already written what they called a delegated regulation act, which is how this is the amendment to the CLP regulation, which will include the PMT vPM criteria, and it's now open for comment until October 18th. But if there's no loud protests from the European Parliament, within a few months, this will become law, these criteria. So it's a very exciting time for me personally, since I've been working with these intensely for the past 5 years. But now I want to go to the final dot in my talk, and that's final dot, the Eawag logo. And that's towards reducing pollution, because this is about what I think we can do. Like now that we know what a PMT is, why it's a problem and how to regulate it, what we can do to reduce pollution. And on this slide here, I got two things. One is the zero pollution ambition logo of the EU, and the other is the emission of Pandora looking at her box. And I think there's like a lot of parallels, because it's the same once you open a PMT substance and put it in the water, you're not going to get the chemical back in the box. And to contrast Pandora, what we have is the EU's toxic-free hierarchy, they call it. This is how they get towards zero pollution. And one way is that you start with safe and sustainable chemicals, for instance, not using persistent ones or hazardous ones. You minimize and control, and you eliminate and remediate. And the favorite strategy is the green one. I'm going to first talk about like different regulations that are related to all these strategies. So at least on the safe and sustainable chemicals, this is where the modifications to the CLP come in, as well as REACH. There's also chemicals like the regulations like the PFAS restriction that are being discussed. So these are regulatory tools that we can use. But there's also regulations about what we can do to minimize and control. One is the Industrial Emissions Directive, which tells industry what chemicals they have to report emissions of. So there's something called the EPRTR register, which would give you that information. So they could add PMT chemicals to that directive, and then we'd have to know more about the emissions. And there's also the Kiev Protocol and Aarhus Convention, which are related, that meaning that the industry would have to know about their emissions and that people have the right to find out about them. And then at the Eliminate and Remediate scale, we have the Urban Wastewater Directive, Sewage Sludge Directive, Water Framework Directive, Groundwater Directive, Drinking Water Directive. This is where we can set our EQS levels, the levels that we can't exceed in any of these types of wastewaters. And how to tackle that is to eliminate and remediate. But this is kind of the last barrier. Ideally, we want to do things upstream. And I'm just going to go quickly through the triangle from the bottom to the top. So related to remediation, where the research and innovation has to go there is towards optimizing treatment trains. And now conventional treatment trains for drinking water, you might have very simple low-cost techniques that are easy to adopt, even in areas with low economies. And this is bank filtration, aeration, sand filtration. These are low-cost techniques, and ideally the only ones that we would want to use. But we do have issues, like, if there's a PMT chemical coming in there, aeration can introduce PMT precursors into the air phase, and with sand filtration and coagulation, you can also get PMT chemicals going to the sludge. But we can also add our new treatment techniques as part of our treatment train. One I'm very interested in is called foam fractionation, which is very effective for PFAS. And that's basically when you, it's kind of similar to aeration, but the point is to make a foam on the top. And all these surface active compounds that are like surfactants and PFAS, they'll all stick to this foam, and you can scrape this foam away. And then you're removing a lot of the PFAS before it goes to the next stage, which could be activated carbon or ion exchange filtration. And if you're doing that, if you're doing a nanofiltration or reverse osmosis, which is particularly expensive, you'd want to do these techniques before that, because the cleaner the water that's going into your reverse osmosis, the less work it is to regenerate your membranes and things like this. But even there, the issue is with all these techniques, they make concentrate. So all your PMTs will end up either in this foam, will end up on your activated carbon or your resin, or in the brines of your reverse osmosis. So then you have to come up with a solution. What am I going to do with that concentrate? And there's also much research being done on this. One of them is to electrolyze or oxidate this brine till it becomes nothing. But you should look at the byproduct formation and energy consumption. You can also regenerate the carbon from activated carbon. You can send it to a regenerator. You can incinerate it. You can pyrolyze it. That's the regeneration. But then you still have to look at the energy balance there. And also you could be introducing chemicals into the air phase that are bad for the environment. So you have to watch what's coming out of your chimney. The final option with these brines is landfilling. And nobody that I met wants to have a landfill of PMT substances in their backyard. So that's not really an option. The next level is to minimize and control. And one thing that is done there in Sweden, they have this thing called source control, and this is where things like the Aarhus Convention or and the Kiev Protocol can come in. And that is where water treatment facilities are actively monitoring for chemicals in their water supply. And when this happens, there's a system that they put in called REVAC, where they get in contact with the water authorities to try to find the source. And then when they identify the source, they try to get all the stakeholders at the same table. Who's the likely polluter, who's being downstream, and they try to come up with some kind of workable solution to reduce the pollution upstream. It doesn't always work. I mean, some people will deny that they're the polluter. It can go to court cases, but it's just a mechanism that can be put into place to control sources. And there's different ways to go about that. One thing that I'm very interested in my research is if we need to advance the concept of substance grouping for removal of PMT substances. For instance, with the trifluoroacetic acid precursors, I kind of want to put them all into one kind of package and see how we can regulate this whole package, because this ultimately has something to do with how much TFA is producing. So I do think we need to not regulate all these chemicals individually, but as a group. And it's the same thing I would say. I want to extend this also to structurally similar PMT substances, because we find that a lot of the triazines, atrazine, melamine, chiromyazine, cyanuric acid, they all have that ring in the middle, like the C3CN aromatic ring in the middle. Can we assume that anything with that ring is a PMT substance, and should we have a group approach for this? This is something that I'm looking into. And of course, we also have to develop our analytical techniques, because the monitoring thing is still a thing. Many of the labs, many of the water sources in Europe are polluted with the PMT substances, but they don't know about that because they're not measuring them. So there's still a lot of analytical techniques that need to be developed, especially related to non-target screening. And there's also different ways we can prioritize these things. So I can look at what's the PMT hazard, what's the likelihood of emission, what's the status of the analytical monitoring gap, can we remediate these substances, are we monitoring these substances? We can look at all these things and we can make a prioritized list of, this is the next thing that we have to work for, because this is the biggest problem Europe is facing now. And I would put here's like a list of some of the things from my assessment that I think that we need the most priority on, that I would like to encourage regulators to put more impact on. And I put things like trifluoroacetic acid, naming benzotriazole, naming these compounds as things that we have to start focusing on in a regulatory and remediatory way. But now let's get to the top level of the toxic hierarchy, and that's safe and sustainable chemicals. One very important issue to do that is to look at issues like, what do we mean by safe and sustainable design? What is green chemistry? For instance, we should incorporate the biodegradability of a substance in the design phase. And so I was talking a lot with people at Eawag today, Catherine Fenner, for example. We were talking about pharmaceuticals and how can they be designed to be, if they're persistent, can they be designed to be less persistent, for instance? That's part of the design. And you can do the same thing for plant protection products that specifically target designing biodegradable plant protection products. I mean, this might affect the life cycle, but it's something that needs to be developed. Another thing is essential use. This is the essential use concept that in a paper from the ETH, Martin Scheringer and Julian Gluga. And they were looking at, are there uses of these chemicals where actually we don't really need them? Like, are they replaceable? And in this case, they had a list of a lot of PFAS where they weren't really needed. For instance, PFAS and chain oil for your bikes. They contain them, but they don't really need to, because there's alternatives on the market that work just as good. So this is one way we can develop it. Another one is to develop alternative assessment approaches. There's different alternative assessment methods like green screen or the OCPA CTSA model, where they look at different hazards in different chemicals like the persistence, bioaccumulation, mobility, and toxicity. But none of them up to now included mobility. But I think in the alternative assessment models and frameworks that we're using, they need to include mobility. And we also need to fill the gap. The biggest data gap we have with chemicals that were being produced right now is we don't know their persistence. There's very few data for all the compounds. I think it's only in the hundreds. I mean, we're producing chemicals in the tens of thousands, maybe hundreds of thousands. And we only have very good half-life data in the hundreds. And so this is a huge issue. So we need some dedicated research and focus on finding environmental half-lives for more substances. And there's some, I just gave an example of one paper where they're trying to simplify methods. And what they did in this paper was they took some of the chemicals that we earlier thought could be PMT chemicals, but we had no environmental half-lives for them. And so they came up with a new method to benchmark their degradation with aniline instead of a 14 carbon labeled compound, which was expensive. And this was a simpler test to do. And the results were they were able to confirm that all these chemicals that we suspected of being persistent in the environment based on their water half-lives were actually persistent. So there needs to be more effort there. We also need more understanding of the mobility of ionic compounds, because the absorption of ionic compounds to soil is quite complicated, and especially at the local level. When I'm talking at a general KLC, we can talk about a typical environment, but at the local level, there could be a chemical that is extremely mobile in that soil, not so mobile in that soil, like mobile in a sandy soil, not so mobile in a peaty soil. But we have to understand these mechanisms better for ionic compounds. And as a sorption fan myself, this is something that I'm quite interested in. And of course, the toxicity gap. A lot of these mobile compounds have not been in the radar of toxicologists and ecotoxicologists because they think, oh, they have rapid excretion rates. You drink them, you pee them. What's the big deal? The big deal is that we're drinking them all the time. So the level that's in our blood is going to be proportional to that. And so we have to think about this chronic general population exposure. We have to think about this chronic exposure in fish, and especially with some of these compounds where the concentrations are increasing, because we don't know, just with the PFAS, why did it take so long to realize what the environmental quality standard is, and why does it keep being lowered? The reason is because we didn't have the tools to identify the toxicity of these substances, and so these tools need to be developed. And one thing I'm saying kind of controversially, we talk about novel approach methodologies that avoid animal testing and toxicity. But I would argue that if you find a substance that's very persistent and very mobile, I would not need to know its toxicity to regulate it. That's why we're having vPvM as a criteria. It's a precaution, because if they are toxic and they are emitted in high quantities, we have a major problem. But just acting on vPvM before you even know their toxicity is a way of managing them in a precautionary way in advance. I also recommend with these chemicals, when we're doing EQS values, that we should, if they do accumulate in the environment like TFA, we should use more conservative assessment factors because out of precaution. It might be that the guideline says, oh, you have so much data, you can use an assessment factor of 100. But if it's capable of global accumulation, use an assessment factor of 1,000 or 10,000 or something like this. So this is how we can fill the toxicity gap, and also maybe try to group chemicals, use more read across. If we can assume that one group of chemical is toxic, we can use read across to include that other chemicals in that group are toxic. And mostly I would like to see more investment. I mean, this is not for the scientists, but this is for the chemical industry and the venture capitalists to invest more in safe and sustainable chemistry. And I mean, we've heard arguments that new chemical regulations is bad for business, but there's been no really empirical data of it, because since the REACH registration was made, the chemical industry has been making record profits each year. They've very rarely had a bad quarter. So they've been able to deal with these new regulations like REACH just fine. And this is an ECHA report that showed that the very first 18 chemicals to be restricted under REACH saved Europe as a whole $290 million a year. So I think the economic case is also clear to do it. But we also have to look at other factors, social factors. We're also working with environmental psychologists who understand how people perceive the threat of PMT chemicals. We find that in regions where there's a lot of PFAS pollution, people know what that is, and it affects their consumer choices. In areas where there's no PFAS pollution, they don't know what PFAS is, and they don't really care about if PFAS is in their product or not. And there's also just these ideas about how to get less consumption. There's also need for material designers to look at ways of making products that do not need these chemicals. And ultimately, we need, I think, like venture markets for green innovation to see this as a sustainable business model, that the future chemicals have to be non-persistent. and non-toxic, and how can we make that into a model more successfully. So that's what we need to do in future. And so just to sum up, I mean, I think we have a lot of tools already now that we can use to reduce pollution of PMT substances. And all you need to do that is love, of course. We also need venture capital to invest in new markets. We need regulations like the PMT, vPvM criteria and CLP and REACH. We need more science and transparency about PMT data and minimizing control. We need to do more source control. We need to have better mapping of the emissions of these chemicals. We have to prioritize especially vulnerable areas that are more at risk from other stressors. And we have to also develop these innovative low-tech treatment trains. Yes, and so now with that, I just want to say some acknowledgements to some of the research projects that we're funding on my PMT work over the years, starting with this water GPI promote project. A lot of funding from the Umweltbundesamt developing the criteria. Most recently, I'm involved in 2 Horizon research projects. One is Perforce 3, which has 15 talented PhD students looking at PFAS. And 0PM is this large project where we have looking at how we can advance all of these techniques that I showed today. And that we're 1 year into that, 0PM. And if you want more information, I'll put some resources on the screen. I'll just say check out the webpage at 0pm.eu. We can get lots of resources on this. And finally, I just want to say that if you want to comment and support on including the PMT, vPvM, criteria and REACH, anybody can do that as long as they're in the European Union, I think. So it might apply to some of you. But have your say, support this regulation. Okay, with that, I'd like to say thank you very much.
Thanks a lot, Hans-Peter, also from our side for this really broad overview over all the things involved with the PMT problematic. Are there questions? Floor is